Cool. So, now that we've discussed enough celestial holography, let's come to something that does work. Let me finally get to a more modern incarnation of twistor theory, whose applications to amplitudes are now fairly well understood. Let me finally tell you what this twistor string is that I have been mentioning since my first lecture. I'm going to tell you a version of twistor string theory, which is called ambitwistor strings. Take another chalk. Ambitwistor strings will be a closely related cousin of the topological B model. Isn't exactly that, but it's a chiral string theory in ambitwistor space. So what is ambitwistor space? Firstly, ambitwistor space PA, projective ambitwistor space if you like. Recall that a twistor ZA mu alpha dot lambda alpha was basically a quantity of the form, for a point particle it was a quantity of the form x alpha alpha dot lambda alpha, coordinatized by the lambda alpha sphere and the position of the particle. Similarly, a dual twistor lambda tilde alpha dot mu tilde alpha was a quantity of the form lambda tilde alpha dot and minus, by convention, x times lambda tilde. And these quantities were defined up to scalings. So, okay, these quantities are defined up to ZW. So, lambda tilde are defined up to little group scalings S inverse lambda tilde. So, under the same action, Z and W together are defined up to SZ and S inverse W. And they also satisfy a very nice constraint that ZA WA is 0, which I checked for you in the second lecture or something, but you can check again immediately. You get this times this, which is equal to this times this, so they cancel each other. So this scaling and this quadratic equation are exactly what will define ambitwistor space for us. Ambitwistor space is a set ZA WA in you can implement these scalings by just taking Z and W to be in CP3 cross CP3 minus, you don't want lambda to be 0 and lambda tilde to be 0, but I don't want to write that again. Oh, I can write this here. Lambda alpha not 0, lambda tilde alpha dot not 0 simultaneously. And you have to satisfy this constraint that ZAWA equals 0. Modulo the, you take this condition is of course a well-defined quadratic equation in CP3 cross CP3. So what's the dimension of this space? You take something in CP3 that has 3 complex dimensions. You take another W in CP3 that has 3 complex dimensions, and you quotient out by that constraint. So this space has 5 complex dimensions. And this has a very nice geometric interpretation, which I'm not going to dwell on. It's basically the space of null geodesics in complexified Minkowski space. Space of null geodesics in C13. And you can check out older books on twistor theory like Ward and Wells. They have a beautiful book called Twistor Geometry something. Or you can check out a review by Tim Adamo on lecture. So there are also beautiful lecture notes on twistor theory. On twistor theory by Adamo, which you can check out, which has this technology of ambitwistor strings described in a much more general manner by taking this perspective that ambitwistor space is the space of null geodesics. I'm going to focus on 4 dimensions. I'm going to use these ZW variables, which are very convenient. So the point is, I'm going to build a worldsheet model, and Z and W are going to act as canonically conjugate variables. Just like lambda and lambda tilde, and mu tilde might act as canonically conjugate. This avoids one of the pitfalls of my earlier models that are only valid in the MHV sector, that I'm now not going to give mu an OP with another mu. I'm going to have a canonically conjugate variable lambda tilde, which will have an OP with mu. So now there will never be any multiple with contraction, so you won't have to put any H bars there. In any case, let's write down a simple string theory into this space of Z's and W's. So if you don't want to think too hard, just think of ambitwistor space as a space of Z's and W's up to that constraint Z dot W equals 0. So you can write down a very simple worldsheet action that looks like, that governs maps. So take a complex coordinate sigma on the worldsheet. So the worldsheet, you take an S2 or CP1, as I've been saying. You write down a simple action to, let's say d sigma complex conjugate. W A P bar ZA. So as I said, W is the canonical going to be the canonical conjugate of the d sigma bar. Now this is the, I'm going to write a chiral theory. So instead of having time derivative, I'm going to have an anti-holomorphic sigma derivative. In this sense, this theory only couples to the complex structure of the worldsheet and the complex structure of the target twistor space. It's also going to be holomorphic. It's also only going to be a theory of the holomorphic coordinates Z's. I'm not going to have the anti-holomorphic coordinates in the game, so it's also going to couple only to the complex coordinates, or the complex structure of the target space. Plus, of course, I have to impose the constraint. So I'm going to have WA ZA as a constraint. So what have I done here? This action governs maps ZA of sigma, WA of sigma from CP1 into the space of Z's and W's, which is basically almost twistor space, which is the space of Z's, and the so-called dual twistor space, which I'm going to denote as PT dual, up to this constraint. Okay, so we're going to deal with this model, and this is called, well, to be proper, this is called 4D ambitwistor string theory, bosonic. This is just a bosonic part. And this was constructed by Yvonne Geyer, Arthur Lipstein, and Lionel Mason. In 2014. So as I said, this is just a bosonic half of a certain worldsheet string theory. And then you turn on worldsheet gravity. In my sigma models there, the action that I wrote down was a genuine 2D CFT. I didn't have any worldsheet gravity there, which is why I can think of that as a genuine 2D holographic dual. Here I'm going to think of this as a string theory, so it's like genuinely living on the full target space because I'm going to turn on worldsheet gravity. So I don't want to describe exactly all the gauge symmetries and all the stress tenses and all. At the end of the day, when you turn on worldsheet gravity, you basically add a bunch of ghosts. And since you have another constraint to impose, you add a few more ghosts, you do BRST. Again, if you don't know about it, you don't need to. You don't need the details. I'll just write down formally at the end of the day. But this basically will give you, what it'll end up giving you will be some factors of volume of SL2C that will come from some ghost 3-point functions in your string amplitudes. And this will similarly give a factor of volume of GL1, which I'll write down in a sec. So there will be some ghost systems there, which I'm not writing down. To compute scattering amplitudes, let's focus on the Yang-Mills case in view of time. In the Yang-Mills case, I'm going to add a matter part to this theory and turn it into a heterotic ambitwistor string. The matter action will just be some current algebra action, which I'm going to formally take to be at level 0. Of course, if you write any genuine current algebra action, you would have some non-trivial level. But what you can do is you can compute stuff as perturbatively in the level. There will be some impurities. You can just drop terms that are proportional to the level. There will be a leading order term which will have no factor of the level, which will give rise to the Yang-Mills amplitude. So I don't need to write an explicit action. All I need to know is that there's some current algebra J of sigma now on the world sheet that governs the OPE FAB. That comes with it's the Kac-Moody algebra of the gauge group that you want to reproduce. So I'm going to take some matter, just like an heterotic string, which will have this current algebra structure. And now I can compute amplitudes from this. Okay. Since I'm not going to discuss BRST, I'm just going to write down the vertex operators. But if you read the original paper, you can show why the vertex operators I'm going to write are the correct objects, because they will be BRST closed. Okay. Let's see. Now, recall from lecture 3 that data on twistor space, holomorphic data on twistor space, corresponded to solutions of linearized free field equations on space-time by the Penrose integral formula. So we have, so in the gauge theory case, you have spin 1. Let's take the helicity plus 1 case. So recall that on twistor space, this corresponds to some differential form, which I'm going to denote little a to mimic the gauge field. It's a differential form along the z bar directions with smooth coefficients, z bar, a bar, which satisfies the conditions that it has homogeneity under these scalings. It scales as s to the minus 2j. What did I do? Maybe I got that wrong. Should be. Maybe I got the formula wrong in lecture 2. So this should be 2j minus 2. Yeah. Because this thing has to have 0 homogeneity for the Penrose integral that I'm going to write to make sense. In any case, this is the correct formula. What happens to me is that sometimes I take j to be negative helicity and then I put a minus there. But okay, this is the right formula. And now what you do, okay, there are two other conditions: that A be a differential form that points along the projective space, and there's another condition that A be holomorphic. So d bar A is 0. That is, in components, dA bar A by d z bar B bar equals d A B bar by d z bar A bar. So if these conditions are satisfied, if you find a differential form satisfying the structure, then this, by the Penrose integral formula, gives rise to a gauge field f tilde alpha dot beta dot of x on space time through the formula d lambda wedge a, this differential form, okay, d lambda is lambda d lambda, and a restricted to the twistor line mu alpha dot equals x alpha alpha dot lambda alpha, then you integrate over lambda in p1, cp1. That's the Penrose transform. So it's natural to expect that if you're dealing with a string theory on twistor space, we should use these twistorial fields to construct our vertex operators. Just like in normal string theory, you construct vertex operators by taking e to the ik dot x and turning that into an operator. Here we're going to take these a's and turn those into an operator. So now we want to construct a vertex operator, and the vertex operator is immediately given by the positive helicity gluon vertex operator is going to be given by V. Suppose we use a gluon index I, gluon label I, and this is going to be given by the integral. So I'm going to write an integrated vertex operator. Integrated vertex operator. Say integrated of the world sheet. So let's just say d2 sigma. The current, there has to be a gauge index. We use B because I use little a and I don't want to confuse you. So there's going to be an element of the current, just like in heterotic string vertex operators. And then instead of using e to the ik dot x, as I would use on a space-time string, I'm going to use a twistor representative A. But now pulled back by that map that governs the world sheet, that embeds the world sheet into twistor space. Okay, good. Now, the trick, the reason why one likes to use ambitwistor space rather than just twistor space is that on twistor space, the corresponding vertex operator would now involve a different kind of differential form, one that would scale with homogeneity -4, and then there's some sort of a chirality in the game. What Lionel and Yvonne and Arthur realized was that if you work with ambitwistor space, then you can build a non-chiral formalism by simply doing some sort of a parity reversal. So you write down, dual twistor space looks just like twistor space. It acts just like twistor space. You can write down a negative helicity gluon, V tilde, B I. So this is positive helicity, negative helicity, by taking the same structure, but now taking A tilde to be a differential form. Okay, so what I've done is you only need d sigma here. The d sigma bar component comes from this differential form and pulled back to the world sheet. So A tilde of now a function of W and W bar, but in a completely analogous way, A tilde will satisfy A tilde equals A tilde A bar dW bar A bar and W bar A bar. Did I put Z bars everywhere? I didn't put Z bars there. This is going to satisfy exactly sort of a parity reversed set of conditions. And partial A tilde A bar by partial W bar B bar equals. So that's it. That gives you a sort of plus minus symmetric construction, which will now resolve the googly problem at the level of amplitudes. We do not know why this works. Okay, now we want to compute momentum space amplitude, so I want to give you explicit representatives for these momentum space vertex operators. Then I'll construct a stringy correlation function, and that will give you all amplitudes on the nose. A formula for all amplitudes. Okay, so Let's see what the twistor representatives little a and little a tilde have to be to get momentum eigenstates. On space-time. So you take, for the plus helicity K, for the positive helicity gluon, the gauge group degree of freedom is contained in the current, the gauge group index. So I'm just going to take a photon and multiply that with J. So for the photon, for the plus helicity photon spin 1 field, the wave function, the differential form is given by, so this is now differential form on twistor space, is given by this very simple expression. So there's an integral over C star scalings, something that pins the external data, so let's give it a gluon index I, this external spin helicity data kappa to the twistorial sphere, but now basically to the world sheet rather than the celestial sphere in the more general case. So this is a delta function differential form. Basically, delta bar of z is, for a complex variable z, is just short for delta 2 of z dz bar. And this is a differential form which contains a factor of ds bar and d lambda bar. So the point being that the ds integral can be trivially done. It's just that it's very nice if you just keep it along. This is a nice representation for the formula. And then there is an exponential which you need to generate. Okay, I'll put the sigmas in when I write the vertex operators. Just as classical functions on twistor space, you have this representative, and you have mu, and you have I. And mu I, you might remember, was just mu alpha dot kappa tilde I alpha dot. Plug this into the Penrose integral formula. Where did I have the formula? Plug that into this formula, and you will see that this delta function will localize S lambda to equal kappa and set mu to x times lambda. Okay, let me just do that explicitly. Let's show you. The field strength on space-time becomes integral over d lambda ds over s delta bar 2 of kappa I minus s lambda times exponential I s mu alpha dot kappa tilde I alpha dot you replace with, you insert that incidence relation in. So mu alpha dot you replace with x alpha dot lambda alpha contracted into kappa tilde I alpha dot. And now basically what this delta function does, sort by definition, is as long as the integrand has the correct homogeneity, it has zero homogeneity in lambda, it simply replaces s times lambda alpha by kappa I alpha everywhere. Sorry, I forgot two derivatives in that formula. So there are supposed to be, okay, yeah, for spin 1, you also have to differentiate a twice. You have to write d squared a, sorry about this, because that's where you get the indices from. Clearly I haven't had enough coffee even after 4 coffees. So you first differentiate this exponential twice. With respect to mu, that gives you I s kappa tilde I alpha dot kappa tilde I beta dot squared times the exponential e to the I s x alpha dot lambda alpha kappa tilde I alpha dot, and you integrate out this delta function that sets s. So you have two delta functions. You integrate both the integrals away, and the s here makes sure that you have the right homogeneities. And at the end of the day, you get these two factors generating the field strength. From here, you set s times lambda to equal kappa I alpha, and you get exactly e to the I x alpha alpha dot kappa I alpha kappa tilde I alpha dot, which is e to the I k dot x. And this is the momentum eigenstate. So this is the correct, so this is how you check that your representative is the correct representative to use. At the level of the string theory itself, you can write down a BRST charge and you can show that the representative will be an allowed representative if and only if it satisfies those conditions. And then since we want to work with momentum eigenstates, we use these specific representatives. Okay. And there are completely analogous representatives in the negative helicity case, which I'll just write down. Quickly for you. As I won't choke. So in the negative helicity case, you get A tilde I W to the bar being, so let's call this S tilde, again integral C star delta bar 2. Now you have something that pins you to the other chiral celestial sphere. In this sense, it's sort of symmetric. So you get kappa tilde I minus S tilde lambda tilde e to the I S mu tilde I. And mu tilde I is now mu tilde alpha dot kappa mu tilde alpha kappa I alpha. This is the other Twistor representatives. Now you basically plug these into these integrated vertex operators, and then you compute a correlation function. You want to compute the endpoint amplitude A. Suppose we want, any questions about the representatives? Unfortunately, this is the only lecture where I really have to go fast, but if you have questions, you should still ask. Okay, but otherwise, just try to, think by analogy with usual bosonic string theory. I'm going to compute a string amplitude, and I'm going to show that that reproduces Yang-Mills amplitudes. So you take amplitudes of particles 1 up to k being negative helicity. You take particles 1 up to k of negative helicity in particles k plus 1 up to n of positive helicity. Such an amplitude, string amplitude, is defined as a stringy correlation function. It's not very stringy because there was no alpha prime, but it is a correlation function. So what I'm going to do is I'm going to label the negative helicity particles by the label L for left. So L running from 1 to k. We tilde L, evaluated as some position sigma L. Oh, sorry, it's integrated, but the integration variable will be called sigma L. And R will denote the positive helicity gluons. E tilde R. And now the point being that since I'm using only integrated vertex operators, I won't be able to saturate all the Gauss zero modes. I have to use, at least in general in string theory, you have to use some fixed vertex operators, but the lesson one learns at the end of the day is having some fixed vertex operators just divides this by certain volumes. So you will have a BC system corresponding to a chiral half of the stress tensor. The whole theory is chiral, so you'll have one BC system, and that will give rise to wall SL2C. Have people come across this kind of wall SL2C in just bosonic string amplitudes? Polchinski chapter 5. You will see where this wall SL2C comes from. And then there's an extra constraint, that Z dot W equals 0 constraint, whose Gauss give you an extra GL1 which basically is the global GL1, the scaling by constant numbers of the twistor coordinates. This is, okay, so this is worldsheet gravity, and this comes from little group scaling. Okay, that's the prescription, and let's compute that. How do we compute that? Okay, now comes the real fun part of the whole calculation. So the amplitude is given, that amplitude, I'm just going to call it A, it's given by a correlation function. Okay, let's take the integrals of the integrated vertex operators out. D sigma 1 up to D sigma n divided by volumes. So SL2C cross GL1 can be combined into a GL2C. Then the correlation function of the currents. So J, say some indices, you put some color indices on the gluon. So J A1 of sigma 1 up to J AN of sigma n. That's the color part. But then there's the dynamics part, the kinematics part. Separates into a nice color kinematics. Anyway, so you find the remaining part of the vertex operator being A tilde L of sigma L, and the other half AR sigma R. Now, the current algebra correlator is standard. It gives you exactly a Park-Taylor-ish factor, which is the origin of Park-Taylor formula. So it gives you, this gives you sum over permutation. So, okay, roughly speaking, it gives you F A1, A2, B1, B1, A2, B2, Bn minus 3, An minus 1, An times the color ordered thingy plus permutations of n minus 2 of the variables, which you can select by choice, where that bracket amplitude, square bracket amplitude, is now given by the remaining part of the correlation function. So you get 1 over, okay, let me just shorten the whole GL2C to 1 over GL2C. And then you have d sigma 1 up to d sigma n. The correlation functions of currents, as you might remember, if you haven't seen this before, the idea is that they have singularities exactly when the currents collide. So they have to have poles that look like sigma I minus sigma j, and then you get a permutation over all those poles. That's this permutation. But in any one term, you get poles of the form exactly like you would observe in the Park-Taylor formula. The sigma 1, 2, sigma 2, 3, all the way running up to sigma n1, where sigma ij is my short for sigma I minus sigma j, using affine coordinates, so that's that.
Sorry, Atul, one question. Do you want to multiply fix the points?
Yeah, that's why I just left it as GL2C. I don't want to go into too much detail into.
So, because usually one has to. I mean, you can.
Yeah, you can set sigma 1, sigma 2, and sigma 3 to 0, 1, infinity.
Does this show up in the Park-Taylor formula somehow? What's the
In deriving the Park-Taylor formula from this worldsheet formula that I'm going to derive, yeah.
Is the numerator factor or is there a point coming from this? Or?
No, it just cancels a bunch of, it just removes 3 of the integrals, 4 of the integrals because GL2C. But yeah.
But I mean, in the Park-Taylor formula, how do you see this?
So it actually turns into momentum conservation.
Ah, okay.
So you have to get 4 momentum conservation delta functions that at the end of the day comes from 4 integrals less that you do to localize some of these delta functions in these vertex operators. So yeah, 4 of the delta functions in these vertex operators will conspire to give you momentum conservation. 4 momentum conservation. Oh, this is GL to C. So as I said, SL to C. This extra little group that you have to impose as a constraint. Yeah. Anyway, this is the Park-Taylor factor. Good. You're on the right track. Park-Taylor factor on the world sheet. Now the kinematics. So the kinematics is now a correlation function in the bosonic theory. A tilde L sigma L R running from K plus 1 to N AR sigma R. And this is the fun part. So you want to compute this correlation function, the bosonic theory, and you're going to do it by a trick that's given in Polchinski. I think it's called the Polyakov trick or something. You're going to take these exponentials in these vertex operators, and you're going to absorb them in the action. Okay, so that correlator, product over A tilde L's, product over AR's, is given by the path integral for Z's and W's. Wall GL1, which you can imagine putting here. Exponential of the action, so integral, so one usually has 1 over 2 pi. D sigma. So I had WA D bar ZA, which is, expanding it out, it's just given by lambda tilde alpha dot D bar mu alpha dot plus lambda alpha, D sigma bar goes D sigma bar mu tilde alpha D sigma bar lambda alpha. Yeah, so we plug that in here. So these are fields. Now you have a bunch of twistor representatives A and A tilde. So you get integral the product over L ds L over SL, product over R dsR over SR. These are your integrals, but you can forget about them. Delta functions, which are again kappa L minus S L lambda of sigma L exponential I SL mu of sigma L kappa tilde L times product over R ds tilde R over S tilde R delta bar 2 of kappa tilde minus S tilde lambda tilde of sigma R just the remaining vertex operator. Almost there. So, now, can someone tell me how to evaluate the path integral? Forget about this bit. Just tell me how to evaluate the path integral when you have a bunch of exponentials. Have you seen this in bosonic string amplitudes? You take these exponentials, you write them as sources. So, you basically use this trick here. Exponential I S field mu sigma LL. You write this as E the ISL integral d2 sigma mu of sigma. Okay, I'll take d sigma mu of sigma L times a delta function that imposes sigma to equal sigma L. Have you seen this trick before? It's called the Polyakov trick. You basically just take this trick, you do that for both of these. So, sorry, I'm just gonna do the same as Prabhar did. I'm gonna replace stuff. So, take that, d sigma L, d sigma mu of sigma L delta bar of sigma minus sigma L. And similarly here you have d sigma mu of sigma R delta bar of sigma minus sigma R. So at the end of the day you seem to get an effective action. So you can take these exponentials inside this action And you can, and then you note the beautiful fact that other than these exponentials, nothing else actually depends on mu and mu tilde. So you can do it, their path integrals. So when you do the path integrals of mu and mu tilde out of these z's and w's, they just localize on their, they just act as Lagrange multipliers and localize on their equations of motion. The equations of motion are just read by reading of the equations of motion of this effective action. So d sigma lambda tilde alpha dot d sigma bar mu alpha dot plus lambda alpha plus mu tilde alpha d sigma bar lambda alpha plus I sum over L SL mu of sigma L delta bar of sigma minus sigma L plus I sum over R S tilde R mu of sigma R delta bar of sigma minus sigma R. So if you don't take away anything else from this lecture, take away this trick because it's very beautiful. I love this trick. So you basically absorb these exponentials, put them together inside the same exponentials. Then all you need to do is compute the equations of motion of mu and mu tilde because they occur linearly in the entire action, so they act as Lagrange multipliers. Those equations of motion give us the final formulae immediately. What are these equations of motion? It's very sad that at Oxford we don't teach this method to our kids in string theory 1. And at Cambridge they don't teach any of this in string theory anyway. Okay, so
did you say that mu is a Lagrange multiplier? Is that some kind of fermionic like kinetic term for mu? Mu tilde, I understand.
Mu and mu tilde both are on an equal footing. Oh, you integrate by parts in the first term, sorry.
Okay. Okay. So the reason why you did the trick is because you want to write the equation of motion for mu tilde, and then you have also the contribution from the other.
Because you can integrate mu and mu tilde out now. Yes. They don't occur in the rest of the correlation function.
Yes. And then now you can reabsorb over the other exponentials inside the equation of motion. I see that's okay.
Yeah. So integrate out mu and mu tilde. That the equations of motion are then imposed as constraints. So the correlation function is done.
Right.
So all we do is impose these equations. So the equation of motion of mu tilde, let me write that down first, is d sigma bar equals, or let me even forget that delta, I'll just write that down as the usual delta functions. So d sigma bar lambda alpha equals 2 pi I delta 2 pi I sum over mu tilde should be there. Which is mu tilde. And the equation motion of mu tilde tells me to get the tilde part. Sum over all the positive velocity particles. Kappa tilde R alpha delta 2 sigma minus sigma R. And similarly, maybe up to a sign, it doesn't really matter that much. You get kappa tilde L alpha dot delta 2 of sigma minus sigma L. But I've just used the fact that delta bar of sigma minus sigma L is delta 2 of sigma minus sigma L d sigma bar. Okay, so these are the differential equations that determine lambda and lambda tilde. And I'm going to find a particular solution. Actually, lambda and lambda tilde don't have zero modes, but I didn't discuss that. So the only solution is actually going to be lambda alpha of sigma equals. So, oh yeah, are you guys familiar with this identity? Delta 2 of the complex number is 1 over 2 pi I times partial z bar 1 over z. I'm going to use that identity now. Have you seen that before? That's how you define a holomorphic delta function. Maybe you saw this in Paris lectures, I don't remember. Anyway, so you basically use this identity here to rewrite these delta to sigma minus sigma r as 1 over 2 pi I d sigma bar 1 over sigma minus sigma r, and similarly for this. And then you compare terms with d sigma bar on both sides, get rid of d sigma bar, and just 2 pi cancels 2 pi I, and you get simple answer. Sum over r, kappa tilde r alpha over sigma minus sigma r. And similarly, lambda tilde alpha dot of sigma equals sum over L, kappa L alpha, this is dotted, sigma minus sigma L. Is it okay if I take 10 more minutes? Okay. Yeah, we're done. So now we basically have finished doing all the path integrals in a gory detail. And we can put the amplitude back together. So you take A equals the worldsheet integral, so 1 over GL to C times d sigma 1 up to d sigma n over sigma 1, 2, 2, 3 up to n1. So this is the color ordered amplitude piece I'm writing. Times what's left. These path integrals are gone, this action is gone, these exponentials are gone. The only thing that's left is these delta functions, and now the path integrals localize on those values, those classical values of the fields lambda of sigma and lambda tilde of sigma. So all I do is take those delta functions and insert these classical values. I forgot a minus sign, but as I said, it doesn't really affect anything. So here's the space-time amplitude for the scattering of k negative holistic gluons. Kappa L minus S L sum over R. Sorry. Yeah, that came from mu tilde. This is tilde. Kappa R. I also forgot the SS. There are also SS here. Sorry for the small font. These SS also sit here. So I have an SR here and S tilde L here. So I have an SR and S tilde L here. So I get SR kappa R over sigma minus sigma R times R running from k plus 1 to n delta 2 of kappa tilde R minus SR tilde R sum over L SL kappa tilde L S tilde L. One moment, what have I done? That's S tilde L and then SR kappa R. SL sigma L S tilde R. Why did I have an S tilde R there? Sorry. That was an S tilde R. As you see, this is a bit of a fiddly calculation, but it's very beautiful when you get the answer. This is tilde. Check the paper. But this, I want to show this because this is a super exciting calculation. This is tilde, this is untilde, and I believe this is tilde. sigma minus sigma r. And that's it. That you can compute this correlative for arbitrary number of particles, arbitrary distribution of helicities. It gives you the exact answer. And now you can, for example, now how do you believe that this is the space-time amplitude? It has a Park-Taylor factor, but does not a space-time Park-Taylor factor. What you have to do is basically evaluate, restrict to the MHV case where you have 1, 2 negative helicity. So A 1 minus 2 minus 3 plus up to n plus. So let me just quickly tell you just in a hand wavy way exactly how this works. What one does is one has a GL2C symmetry which acts on the external data now, and it acts in a very nice way on it acts on sigma, it acts on the sigmas, but you can sort of combine SL and sigma, the SS and sigma R's in a very nice way, so that these should be evaluated at SL. This should be evaluated at SR. Yeah, that's that. Yeah. So you can use GL2C, the division by the volume of GL2C, to fix, so to speak, S1 and S2 to, roughly speaking, 1, and sigma 1 to be Z1 and sigma 2 to be Z2, where the ZI's are my little group scaling. So you can use this GL2C to exactly fix 4 of these things, 2 scalings and 2 sigmas. And once you have done that, the remaining delta functions, so in that case you have, k equals 2, and you have delta 2, so 4 delta functions here. In the MHV case, you have 4 of these, and this turns into momentum conservation by a simple calculation. This bit can actually be integrated out against the rest of the sigmas and I forgot the S integrals. So the S integrals are S1, S1 up to Sn or dsn. You can integrate out the S integrals and the sigma integrals against these delta functions in the MHV case. And that is what happens to localize the remaining puncture locations, sigmas, to, so you do the plus helicity integrals, and that will set sigma I to Zi. That will pin the worldsheet to the celestial sphere in this MHV case. And once you have this pinning, this Park-Taylor factor, sigma 1, 2, 2, 3 up to n1 exactly goes to Z1, 2, Z2, 3 up to Zn1. And the momentum conserving delta function you get on the nose from these delta functions which don't get integrated out. And this results in the MHV gives Park-Taylor. So that's it. We have this beautiful worldsheet theory through which we can actually construct all amplitudes. There are recursive proofs that show you, there's something called BCFW recursion that shows you that this amplitude formula is actually correct. It satisfies all the properties that you expect a space-time amplitude to satisfy, like causality, tree level, unitarity and locality properties that are encoded in them having the correct propagators and stuff. So you can check that it has the correct propagators after evaluating all the sigma integrals. You can also evaluate the answer. People have tried doing that at 6-point MHV, 3 negativity clones and stuff like that, and you get the right answer. So this formula is verified. It resums all possible billions and billions of tree-level Feynman diagrams for you, and somehow expresses it in just one single line. And only a person like Witten can discover such a formula. So that's that. This formula is a sort of variation on what Witten originally discovered in 2003. Lionel, Yvonne, and Arthur sort of found this sort of better, more symmetric, chirally symmetric version, which gives us hope that we can do celestial holography in a fully non-chiral way by taking account both the mixed helicity and the locality of P. These just the final remark, these equations that these delta functions impose are called the four-dimensional scattering equations. So these equations, these constraints that these delta functions impose are called scattering equations. And they were first discovered by Cacciazzo and his students. So Freddy Cacciazzo and Yuan. Suppose this Yuan is the same Yuan that was on the celestial OPE paper. And Song He is in China now, I think, faculty at China, in Beijing. So these scattering equations you basically have to solve, and they're supposed to produce the answer. And okay, the big dream over this coming years or so would be that this nice string theory that is weak dual to space-time perturbation theory. There is a gravitational version of this as well. And one would be able to find some sort of holographic dual of this theory. And that holographic dual might genuinely live on some D1 brane world volume and give rise to some kind of dual, genuinely dual stringy construction of celestial CFT. But we will see. It will take a little while. Okay, thank you for listening. Any more questions? I'm happy to answer. If you like, we could do some discussion later.
Yeah, let's postpone this to the discussion session.
Cool.
And thanks for this nice lecture.